electrical potential energy and potential. Electric field is conservative field, which means that work done in a closed loop is zero. One can define potential energy associated with conservative field. I hope you remember the definition from mechanics. Delta U is negative of work done by conservative force. Now, because this definition talks about change, if we want U at a particular point, we would need a reference point. Often, the reference point is chosen at infinity. So with respect to that, we can tell U at a particular point. And U is of the system. Let's talk about two charges, Q1 and Q2. Let Q1 be fixed and let's move Q2. At an instant, let's say Q2 is at distance r from Q1. Then this will be the force. Let them be positive for convenience. That would help you to visualize, but the result that we would get would be a general result. So this force would be towards right side. dr vector is towards the right side. Q2 is moving towards the right side. So dr vector is towards right. So as Q2 moves, the little work done would be this, F dot dr. F is to the right, dr is to the right. So in dot product we have cos 0. Cos 0 is 1. So if we discuss the movement from R1 location to R2 location, maybe R1 is here, R2 is there, then the total work done would be this. That's it. But this is equal to minus of delta U. So delta U is this. Delta U means U final. Final means when distance between them is R2. That's it. Any questions up to this point? Let me know. All right. Now let us take some reference point. And as I said, normally it is infinity. Reference point means where you are saying that potential energy is zero. UR2 minus UR1 K times Q1 Q2 this. Let us say when R1 is infinity, U is 0. Let R2 be R. So that's the formula for potential energy between 2 point charges Q1 and Q2. If reference point is infinity. If reference point is not infinity, this would not be the answer. Any questions? Let me know.
So can we suppose R2 tends to infinity?
Can you repeat?
So can R2 be infinity?
Can R2 be? You can take whichever one you want infinity. So suppose you want to take R2 as infinity. I mean, that's the way I understood your question. If we take R2 as infinity, then it will be U infinity minus UR1 equal to K Q1 Q2 1 upon infinity, yes, minus 1 upon R1. U infinity is 0. So it won't really matter. Minus minus cancels. So U at R1 is K Q1 Q2 by R1. So it doesn't matter how you do it. Finally you will get the same answer. U at R will be K Q1 Q2 by R. Yes, any other question? Now, if charges have got opposite signs, then this will be negative. And that's what happens in Bohr's model. Proton, electron, so the potential energy is negative. And that's why you get the overall energy minus 13.6 electron volt negative. It comes from U plus potential energy plus kinetic energy. And the potential energy part is 2 negative. Potential energy is always of the system. Though in the context of the Earth, we almost always say that potential energy of the particle is mgh. Technically speaking, it is also of the Earth particle system. So when we say kq1 q2 by r, it is the potential energy of the system of the two charges q1 and q2. Now, what if there are more than two charges? What if there is a system of 3 charges or 4 charges or 5 charges? So when we have a system of charges, we take 2 charges at a time. We take 2 charges at a time. And you know that potential energy is a scalar. So when you take 2 charges at a time, you get some number. And then you take next 2 charges, you get some number. The next 2 charges, some number. And there is no direction involved. Say for example, you have got 3 charges, Q1, Q2 and Q3. Then you will take Q1 and Q2, find potential energy of Q1 and Q2. Then you will take Q2 and Q3, find the potential energy between Q2 and Q3. Then you will take Q3 and Q1, find potential energy between Q3 and Q1. So 2 at a time, and then finally you will add them like numbers. Much more convenient than finding electric field at a point due to several charges. So any questions about potential energy? Let me know. Let's talk about potential now. Consider small q to be a test charge. When it is at A, potential energy of the system is UA. I have shown only capital Q, but there can be as many charges as you wish. When small q was at A, the total potential energy was UA. Other charges should not move when Q is going to B. Other charges could be many. Just to make it easy, I have written just capital Q. But there can be hundreds of charges if you want. When you are moving Q from A to B, this Q, then you should not alter anybody else's position. So when Q was here, the system had this much potential energy. When Q is here, system had this much potential energy. Change in potential energy per unit test charge is called potential difference between the 2 points due to all other charges. All other charges. That means we can talk about potential difference due to a system of charges. Potential difference due to a system of charges. If we define one point as reference point, then we can also talk about potential due to system of charges. Potential due to system of charges. We have talked about potential, we have talked about the field due to system of charges. We have talked about field due to system of charges. Now field was vector. When we talk of potential due to system of charges, then the advantage is that potential is a scalar. So it's not going to be so complicated. It's going to be much simpler when we talk about potential. So due to a system of charges, one can talk about the field at a point, one can talk about potential at a point. Potential has become very popular concept. Potential has become a very popular concept. And you come across potential everywhere. Whether you buy a cell, small cell, or you have got huge normal supply, let me say, you have got normal supply of electricity. How strong it is, a cell or some supply, big supply, how huge it is, we all tell this by using potential, volt. The unit of potential is volt. So here you are seeing it is energy upon charge, energy upon charge. So joules per coulomb. Joules per coulomb is nothing but volt. So this concept has become very popular, and we don't talk about field so much, but we talk about potential quite a lot. Potential is somewhat like pressure in hydrostatics terms. If you see, then water below has got high pressure in a tank, water above has got less pressure. So potential concept is something like that concept of pressure in hydrostatics. Here you can think of it as maybe electric pressure that acts on a charge. Electric pressure that acts on a charge. So if the pressure is more, charge is more inclined to move. So potential concept is somewhat like pressure in hydrostatics. And that has to do with height of the water column. So greater the height, greater the pressure. You can also think of potential as some height. And as you know, it is the height difference that matters. Siphon method, water flowing from one place to the other place. The siphon method is not going to work if both are huge. Both heights are huge and you connect them by a pipe. It won't work. It is not the individual heights that are important, that are as important as the difference in the heights is. Just like that, here also, it is not the absolute potential which is the key. It is the potential difference which is the key. So 420 volt may sound very dangerous, but if 2 points are both at 420, then potential difference between them is nothing. So it is the difference which is the key, not just the value of the potential, because value of the potential is obtained by calling somebody 0, some reference point 0. So one can talk about potential at a point due to some configuration of charges. It could be discrete charges kept at several points. It could be continuous charge distribution, say potential due to a ring at a point, potential due to a disk at a point. So for different charge distribution, you can talk about field, you can talk about potential. So in case of potential, what do we do normally regarding the reference point? Infinity. Normally. This is what we do normally. It's not a rule, it's a practice. Alright, any questions? Let me know. So let's find out potential due to a point charge. Potential due to a point charge. So while here there could be several, here I am considering one and only one. At R, so let's say this is point A, this is B. So as per the definition, I want at A, let us say. Let me write this in reverse order. So VA minus VB will be UA minus UB divided by the test charge. Small q is the test charge. Now since I want potential at A, I would like to call maybe B as reference point. Or why not say that reference point is infinity and B itself is infinity? So we are basically calling B as infinity. But following the convention, V infinity is 0, U infinity is 0. Now one more thing I would like to do before I proceed. If you just look at this step, what is this actually? It is minus of WC but we know that minus of WC is W external agent. So what I'm trying to say is that potential at a point is equal to work done by the external agent per unit charge when the charge is brought from infinity to that point. Potential at a point is equal to work done by the external agent per unit charge when the charge is brought from infinity to the point. Now let's proceed. UA. How much is UA? K, Q, Q by R. So this is the formula for potential due to a point charge capital Q, KQ by R. Any questions? Let me know. If you want to find the potential due to a two-charge system, say Q1 and Q2 at a point, then potential is a number, scalar. Your job is going to be very simple. Find potential due to this at this point. Find potential due to this at the same point and add two of them like numbers, real numbers. Likewise, potential due to three charges, 4, 500 point charges. While we have discussed this for point charge, the result will work for spherical, uniform charge distribution also. Now what if I have continuous charge system? Then how do I find potential at a point? Integration. Suppose we have got a ring. We did this problem for field ring. Suppose we want potential at X. Same situation basically. So how do we find potential now? We take little fellow, so small that it's like a point. Little potential, due to that, let's say the radius is A, then KQ by this distance, it should be DQ, and this distance is under root A square plus X square. In case of field, we could not integrate straight away. Field was vector. So that's a great advantage we have now. We are dealing with scalar. While this is X looking like a variable, we want potential at a fixed point. X is fixed. K is anyway fixed. Integral of dq is a total charge. That's done. Just a word of caution. I have seen students using the formulae for point charge for arbitrary shapes. For example, the formula KQ by R is for a point charge, potential at a point charge. I have seen students applying it for any arbitrary shape. If the charge is spread throughout a pen and you want potential due to that charge distribution at a point, how can you apply that formula KQ by R? You must take some little element in the pen and then you should integrate. Same thing I have seen for field. Now what will be really great is that if we can find a vector using a scalar. Finding a scalar is really easy, as you have seen in this example. You have seen the illustration for field also in the same case, finding field in the same case and finding potential in the same case. In case of field, it was some d vector, then taking component, and look at this, how easy it was. So if we have a relationship using which, if we have potential and we can find field, that can be very useful. And thankfully we do have such relationship. But before we can talk of that relationship, maybe a few applications. How much work has been done in assembling these charges? How much work has been done in assembling these charges? Charges are placed at the vertices, and this is an equilateral triangle. How much work has been done in assembling these charges means how much work has been done by the external agent. WEXT is what is being asked. That should be simple. W conservative is minus delta U and W conservative is minus WEXT. That means WEXT is delta U. Imagine they were at infinity and now they are here. So when we say delta U, it is a final. Final means here, now, and initial is infinity. Infinity obviously means that it is 0. Now, if we want U for 3 charges, then we should take pair at a time. Pair at a time. Say A and B, B and C, and C and A. Right? Now just apply the formula. R is all 10 centimeters. 10, 10. Can you calculate this and see what answer you are getting?
So 234 joules.
Let me see. $234 is the answer I have. $234 joules. Any questions? Let me know.
So 1200 volts.
Let me see. 1200 is right. How did you do it?
So the potential difference will be equal to work done by the external force per unit test charge.
Yes. Work done by the external agent per unit charge. That will be potential difference. It is done against, so it is WEXT. So 12 divided by 0.01. If anybody has any questions, then let me know. We are talking about three charges, all having the same magnitude. All having the same magnitude, this and that. The third charge is placed in the middle of the two, but is moved to this position such that we have an equilateral triangle. That's the final position. Third charge has the same magnitude. So the question is, how much work is done by the field? During the process. Work done by the field means W conservative. Basically, we want W conservative. Can you try to do it? Or let me know if you have any problem. See if that makes any sense to you. So what's the answer?
So it is 3.6 into 10 power minus 3 joules.
Yes, 3.6 millijoules. Any questions? Let me know. You don't have to answer it now. Why does a phonograph record attract dust particles after it is cleaned? So you have to give a short answer for this. That's your assignment. We stop now.